Hello. Um, my name's Chen Qian. I'm a faculty of computer science and engineering at University of California, Santa Cruz. So in this series of lectures, I will introduce some so-called compact data structures that are very useful for systems, algorithms, and protocols designs for computer networks and distributed systems. So I hope every of my students can learn about it so we are able to apply those smart designs of um, compact data structures to our actual work, research, or job, or any other related work. You can find a lot of places that you can apply those interesting, smartly designed data structures. So the first lecture I will give is about Bloom filters. Bloom filters are a type of very well-known data structures. So um, here's my information. I got my PhDs in computer science from the University of Texas at Austin, and I do research in computer networks and network security, cloud computing, IoT, a lot of interesting topics. Um, you're welcome to contact me if you have any questions related to research, related to this lecture. All right. So um, I think you should have some knowledge of about hash functions. So what is a hash function? A hash function is any function that can be used to map data of arbitrary size to some data of a fixed size. So the input is a data of arbitrary size, and the output of it is some data of a fixed size. So here's examples, okay? So suppose we have a hash function, and the input, we are called keys, all right? So the keys could be any data with any size. For example, John Smith, okay? Sandra D, okay? They are our keys, okay? They are with different sizes. But they can also, they can all be the input of a hash function. But the outputs are in the same size. So for example, this output, okay, from 0 to 15. So they are with a fixed size of 4 bits. All right, so 15, that's 4 bits. 1111 is 15. Um, suppose this hash function, it maps the names to integers from 0 to 15. And a well-known feature of a hash function is naming cost collisions. So by collision, we mean that if two keys are different, they may get different values, different results. So in this example, Lisa Smith and Sam D, okay, Sam Doi, they are both hashed to the result 5. So this is called a collision. So what are the common requirements for us for the hash functions in order to be useful? Usually we require the hash function can be applied to any input size key, any size of input key, x. So the x is the input, okay? It should be any size. And it will produce fixed length output d, all right? So d is a output when we apply a hash function to x. So, and the third requirement is that it should be fairly easy to compute d once we have the hash function and we have the input, okay? So it should be easy. And there would be a so-called one-way property. So given, suppose we know the result D, okay, and it should be infeasible to find the key whose result is D. So if we have the result, we may not easily find a input X that can produce D. Okay, so this is called a one-way property. Another property is that so-called weak collision resistance. In details, it means given X, okay, it is infeasible to find Y that HY is equal to HX, which means Y and X produces the same results. All right. So if I have X, you may not easily find another input that may cause a collision. By collision, remember, by collision, we mean that HX is equal to HY. Okay, so a strong collision resistance means it is infeasible to find any XY such that HX is equal to HY. Okay, so this is called a strong collision resistance. Uniformity. Uniformity means every hash value in the output range should be generated with roughly the same property. So in the example we talked about just now, the output range is from 0 to 15, right? There are 16 possible outputs from 0 to 15. What do we mean by uniformity? Uniformity means suppose we have a large number, like, I don't know, 1,000,000 inputs, then we should have roughly equal input that can produce the value 0, and also roughly equal input to produce the result 1, and roughly equal inputs to produce 2. So suppose each input is a bar and each output is a bin, then each bin includes a number of bars, right? So by uniformity, we mean that the number of bars in different bins are roughly the same. So we call it each hash value, like 1, 0, 2, 15, in the output range should be generated with roughly the same probability. Okay. And the red ones, like one-way property, weak collision resistance, strong collision resistance, are required for cryptographic hashes. Okay, we will talk about cryptographic hashes later. Now let's just assume if we don't talk about cryptographic hashes, we may not require those three. Okay, but we do require the others, like uniformity, like ease to compute. So example of hash functions, there are several well-known hash functions. For example, mod. Mod is a very well-known hash function. What is mod? Mod is you divide your input. So every input is just like, if you convert every input to 0 and 1s, and every input can be considered as a big integer, right? So you divide the integer with another integer, like 16. Then you will get the remainder, okay? And the remaining value, to compute the remaining value is mod, right? So the remaining value could be 0, 1, 2, 3, up to 15, if we divide the integer by 16, right? So this mod obviously can be used as a hash function. But is it a good hash function? No, it may not be a good hash function. So we have others. CRC16, CRC32. This is a cyclic redundant check, I think. They also can be used as hash functions. What else? There could be many other more sophisticated hash functions like Jenkins, city hash, farm hash, metro hash, um, developed by by researchers and different software engineers. And MD5, SHA-1, SHA-2, SHA-256, these are cryptographic hash functions. Okay, so they have some properties like collision resistance, all right, and the one-way property. But those city hash, farm hash, metro hash, they may not have strong collision resistant. All right, so that's so much for the basic knowledge of hash functions. We will talk about Bloom filters. Let's look at what a Bloom filter is designed for. All right, so this is a post I wrote to a Chinese forum, and this forum is called the Chinese. It's not a forum, but just like it's a website which called Zhihu, and Zhihu is similar to Quora in English. Okay, so in the English world, people will post their questions and answers to Quora, but in Chinese, in China, people post their Chinese questions and answers to Zhihu. So the question is, which data structure do you think is prettiest, the most beautiful data structure? So my answer is first Bloom filter. Okay, Bloom filter. Many PhD students used Bloom filter to graduate. Okay, to write their dissertations. And also cuckoo hashing. Cuckoo hashing is another data structure that we will talk about in this lecture. So why Bloom filter is so beautiful and is so useful? Bloom filters are used for membership query. So what do we mean by membership query? Suppose we have a set S, okay? S includes a big number of members, A, B, C, D, and we want to know if given a element P, is P a part of S, which means is P included in S? It's a very kind of like straightforward, but not very easy to solve. And a Bloom filter is a simple space-efficient randomized data structure that to solve this question. A Bloom filter represents a set in order to support membership queries. And the author, Burton Bloom, introduced these Bloom filters in 70s, okay, more than 40 years ago. A standard Bloom filter represents a set S, and S includes n members, x1 to xn, by an array of m bits. Okay. In addition, we use k independent hash functions. So there are three important parameters: n, m, and k. The assumption is that the hash function should map each item to a random number uniformly over the range 1 to m. Okay, so we have an array of m bits. That means each hash function should map the item to a random position on this array. Okay, so here's the array. We have m bits. Each bit is either 0 or 1. Initially, we set all bits to 0. So assume we use k equals to 3, which means we use 3 hash functions. And we want to insert a number of members in the set. and to build the Bloom filter. So at the beginning, those bits are all zeros. Then once we insert x1, the 3 hash functions, remember case 3, the 3 hash functions maps x1 to 3 random positions. And we set those positions to 1. Okay? So next, we insert x2. Again, x2 is mapped to 3 random positions. And those positions are set to 1. So if the random position was 1 before inserting x, it still becomes 1 if we insert x2. So by inserting x1 and x2, we'll have 5 positions being 1, and the others are 0. Okay. So next time, we want to query an x. So we have built the Bloom filter. Bloom filter looks like this. Okay. So next time, we want to test whether x2 is in the set, right? So to test x2 is in the set. So we map x2 to 3 positions of the bitmap. And we will find for all positions, the bitmap, these 3 bits are set to 1. Okay, so we may conclude that x2 should be an element that has been inserted to the Bloom filter. So we conclude that x1 is one of the element of the set. If we query, so if all ones, x2 is a member. I'll query a y1. y1 is not a member of the set, so we call it an alien element. And y1 is not a member. So y1 is mapped to 3 random positions. And we find that only one of the position is 1. Okay? If any of the position is 0, then we conclude y is not a member of the set. Okay, why? Because if y is a member, all right, then those positions must be set to 1. But now we find some position is not 1, right? It's 0. So we are able to conclude that y1 is not a member. This logic is very clear and very easy to understand. And in testing, okay, and experiments, we may have several concepts. Suppose this circle includes, all right, sorry. The left part is a set, right? And this circle is a testing method. And the testing method will report you the result, either true or false, or positive, negative. However, this testing method may not be 100% accurate. So in practice, we know that it's really, really hard to find a 100% accurate, 100% accuracy for any testing method. So the test will report positive, okay, within this circle. And those positive ones, and which is also the relevant ones, which means the true ones, are called true positive. And those positive results, which does not actually belong to the true results, are called false positives. False positive means it reports positive, but it's actually not. Okay? So it's called a false positive. And a false negative means those are relevant elements, but they are reported as negative by the testing method. So this is called false negatives. So both false positive and a false negative are harmful, okay? But true positive and true negatives, they are correct. So Bloom filters have false positives. Why? Look at this example. We have inserted x1 and x2. Now, there's alien element y, and we want to test whether y is in the set. But y is a lucky guy. It maps to 3 random positions, but very luckily, all those 3 positions are ones. Okay, they are ones, not because y has been inserted. It is because x1 and x2 are inserted, and y happens to have 3 collisions on those bits that are mapped by x1 and x2. So y is a really lucky guy. So we conclude, based on the testing result, we conclude that y is a member, but it's actually not. So this is called a false positive. However, there's no false negative. That means if we do a Bloom filter, and the Bloom filter tells us that the key is not a member, then the key is not a member. There's no false reporting. Okay. So there is a clear trade-off between m and the probability of a false positive. Obviously, if m is larger, then an alien element has less probability to cause collisions. So it has lower false positive rate. Okay, or we call it probability of a false positive. That is false positive rate. So we can do some calculation. Suppose we have n keys, m bits, k hash functions. After inserting m keys, let p denote the probability that a particular bit becomes 0. Then p can be calculated as using this formula. And I don't want to explain it in details, but from the formula, we can find that if the p is related to k, n, and m. So if f denotes the probability of false positives, and f is equal to 1 minus p to the power of k, and it can be converted to this equation. And if we want to minimize the false positive, we may get a k, which is equal to lines 2 times m divided by n. At this value, f achieves optimal value. That is a minimum false positive rate. But overall, we can see that the false positive rate is related to m, k, and n. So obviously, if m is bigger, then the false positive rate is smaller. All right. If k is bigger, the false positive rate is also smaller. Not really. K is kind of like has the optimal value. Sorry, it's not a bigger the better. And n, when n is smaller, then the false positive rate is smaller, right? Okay. So an obvious disadvantage of Bloom filters is that it does not support deletion. So why? Say we have inserted x1 and x2. We set the corresponding bits to 1, okay? If we delete x, suppose we delete x1, then we want those bits to be back to 0. So we set it to 0, 0, and 0. All right. After that, we find that one of bits of x2 is set to 0, but it actually should not, because x2 is still a member of the Bloom filter. A set. But if we set the bits to 0, then using Bloom filters, we test x2. It will tell us that x2 is a non-member, which is incorrect. So Are the features of Bloom filters? The Bloom filters has low storage requirement. You can do fast membership checking because that only requires you to compute 3 hash functions. Takes you all of 1 time. There's no false negative. There's false positive, but we can somehow control it to be a low value, and no deletion is allowed. So this is the basis about Bloom filters. Okay, so we first stop here.